Example 5.8. In this example, we have a syringe which is used to inoculate a cow. The plunger has a face area of 500 millimeters square. The liquid in the syringe has to be injected steadily at a rate of 300 centimeter cubes per minute, and it has a leakage passed through the plunger, which is equal to 0.1 times the volume flow rate out of the needle. We need to determine at what speed should the plunger be moving to meet these conditions. For this problem, the control volume is given by this boundary. We have two control surfaces, which are both an exit control surface. In both cases, the velocity is constant, and this is a case of a deformable control volume, in which the length L changes as a function of time. This change of L as a function of time is equivalent to the velocity of the plunger. In order to evaluate this type of deformable control volume, we will use similar steps as the one used in a unsteady case. So we start the analysis with the continuity equation for the control volume, which is the Reynolds transport theorem for mass conservation. Since this is a deformable control volume, this term cannot be neglected, and then we could simplify this term as the summation of the mass flow rates at each one of the control surfaces. So in the same way as the unsteady case, the first thing that we need to do is solve this integral, and this is going to always reduce to rho times the volume that we're going to have, and this is going to be equal to the mass flow rates at 1 plus at mass flow rate at 0.2, and both of them are positive because they are outgoing mass flow rates. We need to determine the volume of the control volume, so that is going to be given simply as the cross-sectional area of the plunger times the length, in which this term is constant and this one is the one that changes as a function of time. So we substitute it into this equation, and we set d dt, and that is going to be rho AP L and plus m1 plus m2 is equal to 0. Rho and AP are constant, so they could get out of the derivative, and this becomes rho EP dl dt, and that is going to be equal to minus mass 1 plus mass flow rate 2. Therefore, dl dt, which is the velocity of the plunger, is going to be negative m1 m2 divided by rho AP. Notice that for this particular case, the change of L with a function of time, it is negative, is because the value of L reduces as a function of time. If we substitute the values that we know into the mass flow rates, we find that this is going to be minus rho Q1 plus rho Q2 divided by rho AP. Since the density does not change, we could cancel it in all locations. Therefore, the velocity of the plunger is going to be negative Q1 minus Q2 divided by the area of the plunger. Knowing that the value of Q1, which is the leak value, is equal to 0.1 Q2, and we substitute into this equation, we could find out that the velocity of the plunger is equal to 660 millimeters per minute. Notice that the direction of this velocity is going to the right, and if we evaluate as the rate of change of the length as a function of time, we set to be negative because the length is reducing with time.